Gonna change the order? Cheated. I'm cheating? No, I'm not cheating. Because we definitely need to get, this is a good time to go ahead and talk about this example, because we just saw this notional example with the 8 directs and the single indirect, what we call indirect, okay? Let's go jump to a real Unix example, okay? So I have these at the end, so those of you who are looking on the slides, this is the last 3 slides in the slide deck. Okay, so in the Unix v7 directory, it's a little bit different, but it's not too much different. We have the inode number as part of the address, and then we have the file name inside the directory. Okay? So in our file system, as an example, we would have like the root directory. We would have, oh, by the way, we have 2 file names. Every directory file has 2 file names, and they are the same thing. And they're dot and dot dot. Dot means this directory. Dot dot means parent directory. All right, so anytime you're in a directory in Unix, Linux, you do a cd dot dot, you're going to go to your parent directory. You can do a cd dot, and you can come to your current directory, which really doesn't seem all that useful, but it's important because that's where you're going to have your own address. So if you need to know your address, it's simply the first entry inside of your directory table. Okay, so dot, dot, dot are always self and parent. Okay, that's good enough. So then the rest of the entries are all the other files that you create. Here's where you would have the inode number of file bin. And the file name for file name bin is here in the directory file. Dev starts at 7, live starts at 14, etc at 9, user 6, temp 8, and so on. Okay? Same thing in slash user. Slash user was 6, so there you see 6 is self, parent is 1. So you can see it really works. And then it has these files with these inodes for each of these files. Okay? And then we have this user AST. Now this example is useful because when you are trying to change working directory, go to this particular directory path, it's going to do exactly this. It's going to go to directory node for slash to find user. Directory node, we always know it's 1. Find user, it is 6. Now, we go to the inode for 6, and we see that block 132 is the address I need to go to. So there's my physical address, and there's my physical map. Okay? And then, if I still need to traverse this path, I need to go to AST. I go inside of slash user, which is in block 132. I find AST. There's a file name, AST, and I have inode number 26. So I go grab inode number 26, and there is the block number for the first block, 406. So that's AST. I still need to get to inbox, so I go find inbox, and it is inode 60. So I just go to inode 60, and it has the address for first block in inbox. I am there. Questions? Pretty straightforward. It's exactly what we talked about, right? And here's a real-world example and how it actually works. Then there's this diagram. This diagram is the way inodes are set up in an earlier Unix system. Pretty much the same way they're set up today. Okay, you have the file attributes, which has date created, owner group, all that fun stuff up in the attribute section. And then you see 10 direct addresses. Then you have 10 direct addresses. Okay, so in the previous example we showed a simple 8. Here we have 10. Okay, again, we have to define what the size of a block is before we can get this far, so all of our blocks are the same size. And maybe they're 512, maybe they're 1024, whatever they happen to be, they're all the same size. Let's use 1024. Okay, so if I have 1024, I could go out and create 1024 or 1K if I want to. Just roll it up and use an estimated number. I can say, oh, 1K. 1K times 1K, right, is how much?
$2K.
1 megabyte.
Work on that one.
2 to the 10.
2 to the 10?
2 to 6.
2 to the 9 was 512, 2 to the 10.
What's
2 to
1024 is 2 to the what?
10.
10.
Okay, so 2 to the 10 times 2 to the 10, wait, it's not 2 to the 10, it's 10 times 1024, right? Boy, you guys are letting me get away with anything here. So what's 10 times 1024?
10.
Oh, I see, I added a 0. Right?
1,048,576.
1K to 10, 1K to 10K. 1K to 10K.
Yes.
1024 times 10 is 10K. Thank you. So I use the simple number like 1024. It's easier to work with than 512, right? Yes. Okay, so I can create a 10K file using my first 10 direct addresses. So now I have this thing that I'm going to call first indirect. That block is called first indirect. And just like in our previous example, we're going to take this 1024 size block and we're going to divide it up into 4 chunks. So I can create how many addresses? Specifically?
256.
Yeah.
Yes.
So I create 256 addresses. 256 is 10 to, is 2 to the what?
2 to the 8, yeah.
8. And I have each one of these pointing to a 1024 size block, right? So how much would this block be able to point to?
260,144.
10, which you said was
It's
approximate.
approximate is like 260,000. Rounding down, I guess would be an approximation. Do you want like an accurate figure or?
Well, we can go along with the
260,144.
10 is 1K, 2, it would be 2K, 4K, 8K, 16K, 32K, 64K, 128K, 256K, yeah,
That's the approximation.
that's an approximation. So I got 250, so with my 10 filled up and my first indirect, I can get 256 approximately KB plus 10 approximately 1024, 240 KB, 240 bytes would be the largest size file I can generate with the first indirect. Is that big enough? Nope. So what's going to happen next is that as soon as I get my 256 here, right, I'm going to say this file is growing much faster now. I need more. So this next one here we call second indirect. And what it says is that I'm going to point to 256 data blocks, and each of these pointers is going to point to another block that I'm going to make as a second level dereference. So I'm going to have an additional 256 pointers
Per block.
per block.
And each one of those pointers points to 1024.
That's right.
Good lord. Large.
Now I can get large,
Yeah.
and we can calculate exactly how large, can't we?
Yeah.
And if that's not large enough, then I go to this next one, which I call third indirect. And it's going to do, we have one more layer, one more level. Here's my first indirect block, which is pointing to 256 second level indirect blocks. And each of these are now pointing to a third level of indirect blocks. 256, 256, 256, 256, etc. Okay?
So 17 gigs.
It's huge. Now you can get to a large file. Yes?
Is there a max number of indirects? And how high can we go?
Well, in the Unix file system, they use triple indirect as the largest. And if they say you need a larger file, then one of two things happen. Either you make larger data blocks, or
Segment file.
we'll save the other discussion for another class. There's some other things you can do for some occasional larger files. But for here, we just want to study this, because this is how almost all files are addressed in the Unix Linux system using first, second, triple indirects. And yes, I would expect you to be able to calculate the largest size file given a structure like this and a known block size. Yes.
For the exam, like, do they need to be accurate figures, or can we do approximations like that?
If you do approximations, then I would want to see the actual work.
Of course.
You wouldn't have to solve it, you can give me an approximation as the answer, but the full work would need to be.
That's like that.
So questions? Okay, then we'll go back to where we were, which was 21, which was. See, wasn't that similar? Just real numbers instead of this old example. Okay, actually we just saw this, right? So a directory node, what does it look like? Well, it has the inode pointer and it has the file name, right? And the thing is, the inode pointer, okay, we know that we can go there and it's going to have attributes about the file inside the inode itself, and then it's going to have the pointer to the data node. Now that's how the Unix Linux system implements it. There are other ways you can implement that. So coming back to the theoretical side of the discussion back in the main chapter, is that the directory node itself can contain the file name and attributes if the attributes are small enough to fit within your a single record. You could do that, okay? Or you can make this the pointer to the inode itself, which then contains the data. So if your information, your attribute information is small enough, you could actually put that in the directory files record, each record itself. But today most systems, we just use inodes, and so that makes it easier, because then we could get the real needed information instead of limiting it to make it fit inside of the directory node itself. Okay? Now, file names, unless you go back to like DOS days, you know, they have nice long lengths to them. You could come up with some pretty creative file names, because most systems today will let you create long file names, unlike the 8-character position .3 that you had in DOS, that early Windows systems kept on. So if you're going to have lengthy file systems, you can also introduce inefficiencies. Okay? Storing the length of a file name itself becomes somewhat interesting, because you can have a file name with a single character dot three character file extension, or you could have, the full 29 or whatever your particular operating system restricts you to. And then you're also wasting space, by storing the same characters over and over again if you have repeats and stuff like that. So most file systems today actually hash the file name, just so you can gain efficiency. Okay, and that's what this is talking about here. We're also talking about this. So you have your length of your file name, you have your file's attributes itself, okay, for each file, and then you can either store the file name directly like you see here, or you can use a hash structure and put your file name in a heap itself. Okay, so then you can just put your pointer in there, and you can grab some efficiency. So I'm not going to worry about how to actually do that. I just wanted to bring that up as that's one of the efficiencies that you should be aware of that most systems are implemented today. Okay? Now, what you do need to understand now is that of shared files, particularly because shared libraries are in such wide use today on every operating system that there's this huge efficiency there for one thing, so we need to understand them. And we also need to understand how we can be efficient in the file system by having something like this. Okay, so what I'm going to talk about now is that is how we can implement a shared file. So first off, a shared file actually belongs to a particular directory node, just like every file belongs to a particular directory node. And as a reminder, please, eat your meals before class, during break, or some other time, but not during class. Okay? So, shared files. First off, they actually have to belong to a directory file. What I want to do, though, is I want to have the ability to allow multiple directory files to access this shared file. Some of these efficiencies we're talking about is in the vein of, if I'm going to a location that's somewhat frequent, that I'm going to frequent a lot rather, then if I had a shortcut to get to that file, that would be an efficiency. Okay, so that's one example. So in this case here, if I'm normally traversing into this subdirectory here, instead of having to go all the way up to root and down this path here to get to this file, because remember, I'm looking at the directory file, I'm looking at the pointer to the inode, looking at the directory file, looking at the pointer to the inode, right? I'm doing all of that to get to this location here. But if I'm already here and I go here frequently, I want to be able to have a shortcut path directly to that file, okay? That's what we're talking about with sharing files in the file system itself. So to do that, I want to create this link. I want to create a link to not this path, this traversing mechanism that we've been talking about, but what I want is the inode number, right? That's how I get the link, that's how I can establish a link directly to this file, is by its inode number. Which means, yeah, I've got to visit it once, go down this path here, visit it once, so I can get its inode number. But once I have its inode number, if I have the ability to obtain that number and then associate that somehow with this directory file, then I could do this shortcut path type of approach. That's kind of the goal here. But there's some things I have to be concerned about when I create this linkage. One of the things I have to be concerned about is, we'll keep going back and forth, one of the things I have to worry about is if I can create one link, I can create multiple links. I can create a multiple link here. I can create links more than once, twice, 3, 4, I don't know. It's dynamic, right? However I want to create links, I want to be able to do that. Problem is, if I allow just anybody or any number of directory files to link to this file, and I want to delete this file, I need to know what other files think that they're linked to this file Because if I suddenly make it go away and see the owner, right, then what are these other directory files doing? I have to be worried about consistency. So to do that, what I'm going to do is anytime I create a link to a file, I'm going to have a new attribute. I'm going to have to add an attribute called count. And what count will do is it will keep count of how many directory files have linked to this file. Because if count is 1, then that means the one directory that created it, okay, that's the only one that's linked to it. So this directory file can safely delete this file, and the rest of the file system consistency is intact. Does that make sense? Okay, so I have my owner, I have count equals 1, I can delete it, not a problem. But now if B decided it wanted to link to that same file, owner is still C, if I increase the count to 2. I now have 2 directory files that are linked to this file here. So that's good so far, so good. But now, if I decide to delete this file, I still can. I'll let this happen. And I don't care if it was the owner. I don't care if it was C. I don't care if it was B. Either one of these deletes the file. If it's B, it's deleting its link. If it's C, it's deleting the actual file. Well, in this case here, if C was trying to delete the actual file, since count was greater than 1, and C was the owner, then what I need to do is shift the owner to B. Well, this says C here, but I need to shift the owner to B and decrement my count. And then, because it's 1, if B at this point here decides it wants to delete it, it can do so, and everything would be consistent because count was 1. Yes?
That should be owner is B, right?
Yes, that's what I just said. The error in the slide that owner should have changed to B when that happened, because C was the one doing the delete. Okay, so if it was 3, if it was 4, it was 5, I'd simply just go ahead and decrement the counter unless it was the owner that was deleting it, and then it gets shifted over to another node. You gonna ask?
Right, that's my question.
Right? Make sense? Okay. Yes, journaling file systems, we're going to talk about this in the next chapter. So some reading in your chapter about journaling file systems. You may wait until the next chapter. What I want to talk about next is virtual file systems. We're talking about HFS, hierarchical file systems, which was a virtual file system in the sense that we weren't working with physical addresses. We were working with addresses of data blocks, but those are real addresses. So that's the distinction. HFS, we're working directly with one file system. However, virtual file systems is kind of a goal here, because a virtual file system will allow us to take multiple file systems and create one virtual file system from it. And this is what you're seeing on Rohan every time you log in. If you're looking at your directory structure, if you do a DF, you'll see the listing of all the different file systems that are mounted at this time in Rohan. And what it's doing is creating one virtual file system, so you can navigate through all of these other file systems as if it was just one virtual file system. We do that by go ahead and creating the actual file systems themselves, and then we're going to create this thing called a mount point, which allows us to take any of these file systems and attach it to / or any other directory below / as a mount point, and say this is where this particular file system enters into the virtual file system. And then all of the navigation will be done the same way as we were doing in the files HFS that we're talking about, but it would be from that mount point below. I have some examples of that here coming up. In order for us to do this, we're going to have to define those interfaces. We have to create these file systems, and we have to worry about how we're going to manage this cache for the buffer system. The key thing here is that from the user's perspective, they're accessing the POSIX Systems calls the virtual file system, which is going to translate to these addresses for the underlying file systems that the virtual system is mapping to. Okay? So to do that, we're going to create these process tables. So to do that, we're going to have the process tables like we had before. We'll have the file descriptors, but now they're going to point to these vnodes. Okay, and the vnodes are basically the file system nodes mapped to the virtual file system. So we'll have that translation in there so that I could then do, instead of my physical file descriptor being mapped to the inode of that file system's actual inode, it's going to be this virtual inode that then gets passed as the translated inode for the underlying file system. Seems to lost looks. Let's try a diagram. So in your process, you have your file descriptor table, right? 0, 1, 2. Those are those special files you get when you create a process, right? They are
Standard in, standard out.
correct. And then you have your other entries here, okay? And there's your file pointer. File pointer, I drew it linearly before. There we go. I will draw it linearly again so that, there we go. So my file descriptor table is a file pointer to the file's inode, yeah? And file system X. Okay, so when we were talking about our file descriptor table before, that's what we were talking about. We have a pointer now to the file, which we now know is the inode, right? But now in our virtual file system, we're going to add this complexity because I no longer want to point to the actual file system because I now have multiple file systems. File system Y, file system Z. So instead, I'm going to put all of these into this virtual file system. So instead of pointing to the actual inode here, I want to point to the vnode. So this pointer is now a pointer to this vnode. And what's this vnode? Well, it's going to have the starting address for each of these file systems. And then it's going to have a mapping from that to the offset inode inside of each of these file systems to get to a unique entry inside the vnode table. So that instead of pointing to a single file system's inode, I'm now going to be pointing to an entry in the vnode table, which has this mapping to file system X, Y, or Z, in this case X, and its inode number to get to that specific file pointer. That's what that's saying. Yeah.
It's like a practical application of this, where you have multiple, no, I mean, did you talk about journaling systems yet, or was that part of this?
So the journaling systems, I said we're going to look into that more in the next chapter, so we don't need to know too much about that, other than, yes, we are journaling systems. What we need to know here is that we're going to create this virtual file system, and I'm just concerned about this aspect of it, not the
Yeah.
details of implementation.
Well, I know that, but like, what is the actual, who implements this? Like, do a modern, is
Yes,
oh, it's
Unix, Linux, all do it this way, and as does, oh, wait, it's the time. Windows, the current Windows file
Windows
system.
NT, or NTFS?
NTFS thing.
So I mean, but like, is it like a plug and play thing, or there actually are like actual physical, like virtual file systems within your, like your main disk?
So this is in memory space.
Gotcha. I mean, I can figure it out.
Okay, so let's implement a memory space here. So that's why we're going, because we're accessing these all the time from multiple processes, right? So we need to have some memory space, memory residue. So that's what we're getting at here. My process is file descriptor table is now pointing to these vnodes, which I could then get to specific file system in its inode to do that read, write, open, close, create, delete, whatever operation. Okay? No questions? Yeah.
In the vNodes table, you said it just really much stores the index into file system, whatever that points to that particular inode on that file system.
So when I go
Exactly
to,
into that entry.
let's say I want to open a file, right? So if I want to open a file and that file happens to be in file system X, okay? In a virtual file system, I'm organized by file system and then my entries inside of it. So I have my individual pointers to all my inodes, my addresses, if you will, of each of my inodes by file system is in my vnode address. So in my file descriptor table, when I go to do an open, it's now, instead of going to a specific file system directly, it's going to go to the vnode tables, and it's a pointer going to be a pointer into this table, which then has a pointer to which file system and its inode. Any other questions? Does this make sense? Got questions? Okay. Okay. We kind of jumped ahead, so this is going back again, the theoretical side of it. One of the things, and there's a couple things we still need to talk about regarding disk space management, and that is block sizes. Choosing block sizes seems like a trivial thing, yet it's part of the tuning of your particular file system, and therefore your particular system that you are hosting. For these general purpose machines that we're using on a daily basis, it's not as big a deal. The defaults that they've kind of settled on are good for most cases. What we're concerned with mostly is when we have like a growth, suddenly we have more memory or we have different kinds of disk systems, that's one thing. And the other thing we're concerned with is you might be tuning a specific system for a very specific purpose. Okay, like when Google was standing up its data centers, and when they were determining, oh, we're going to host 40,000 machines and we're going to host 8 million drives inside of this data center. So then it was a really big deal what size their blocks were. And it was based upon what is the normal, nominal, and largest file and smallest file sizes that the users were creating and how frequently. Because all of that's going to affect performance, both in speed as well as in efficiency of use of the file system. Because as you saw earlier, if I have data nodes that are only partially filled, I am wasting memory because I can't let another file share that data node, right? So the emptier on average they are, the more space I'm wasting. So if I'm wasting a lot of space, then maybe instead of a 1 meg size block, maybe I need to go down to a 512. Now, if I'm creating lots of really large files, then maybe not, because of all of the different blocks that I'm adding and deleting at any given time. There's a lot of work with that. So I might want to reduce the work and make them larger blocks. Okay, so this is one of the things that you would think what your author was discussing, but it was also discussing things like latency. How long does it take to open up a data block when you're doing it directly on the file system, when you're doing it through a virtual file system, or when you're doing like a network access. Okay, and you're moving the blocks over a network to get your virtual file system distributed. because that's what we do with a lot of, with a lot of virtual file systems, is we make them distributed. Several servers could see them and operate with them and share them, okay? Then you have to worry about latency with it as well. Larger blocks, larger latencies, right? Significantly larger latencies in some cases. So he did actually a fairly decent job discussing this graph in your text, so you should read it. The idea of being here is that what you want to do is you want to look at the time versus space management, right? You're looking at time versus space. How much wasted space, how much wasted time you have. What is this system being tuned for? Is it being tuned for time performance or space performance? Or does it need to be where that balance is? You can easily see, oh, it kind of balances here, right? That might be your sweet spot. But if you don't care about network latencies, then that's not the place you're interested. Questions? Data block sizes are a big deal. Like I said, to tuned applications that have specific purposes. I use the Google Data Center as an example, but there's many others. There's computational centers, right? Some places you go to, like where high performance computer assets are stored, and you got remote access to high performance computers. So if a lot of your work is algorithmic, but you're doing a lot of front end loading with lots and lots of data, or if it's while the algorithm's running, you're also generating more data and calculating more data and storing it and stuff like that, then your data sizes might be tuned differently because you're more concerned about performance throughput and somebody else can worry about managing empty blocks or partially used data blocks later on. And typically with data files, you're not wasting that much anyway because it's always in the last block. So your tuning requirements may be differently in that type of situation. Okay? It's always about the requirements. Just like any job you might get if you're going to software engineering or software development, it's always about the requirements. Everything's about meeting the requirements with the best efficiencies you can based upon the requirements, not based upon your preferences, and not based upon your, I always like this sort of algorithm best, we're going to use it. It's the right solution. I know it is. Do I know the requirements? No, but it's the right solution, right? You'll see some of that out there. It's out there, believe me. But it's always about the requirements. If you always go back and you're looking for establishing your efficiencies or determining where your efficiencies should be focused on, whether it's data block sizes or algorithm selection, go back to the requirements every time. Okay? Okay. Somebody asked me earlier about the free list. Who was it?
I was talking about it, you
Oh.
brought it up.
Okay, so let's talk about the free list. So the free list is where we're going to contain all of our unused data blocks and inodes. There's also going to be a free list of inodes too, by the way. So we're mostly interested in the data blocks because there are so many more of them, and they are the ones that are coming and going the most frequently, as you saw with all our single, double, triple, indirect stuff going on. There's lots of data blocks flying around, coming and going all the time. So coming up with an efficient free list management system for that is going to be very important, right? So there's a couple of different approaches, as you might guess, on how we can do that. One way will be storing them in a linked list, right? So that's what this shows here. So if we have 1024 byte disk blocks handling 256 382-bit addresses, because that's something here, right? Okay, I can go ahead and store all of my free data blocks inside of an indexed list, and I simply insert delete, right? All I have to do is insert delete, and I can insert my data block when it's freed up into the free list, and then I delete, giving that data node to the requesting process a data node by deleting it from the free list. Okay? So insert, when a node becomes free and I'm putting it on the list, I do the insert, I insert the block number for that free block of that data block that I just freed up. It's now in the free list. Delete it, I take that node number out, give it to the process that says I need another data block. There's your data block, and you now manage it, and you delete it from the list. So insert, deletes, copying, deployers, all that stuff is pretty good, right? It's pretty simple, pretty straightforward, and it works. We used this for quite a while. But we also realized that we can improve upon this. We can make this faster simply by using a bitmap instead, right? If we have every bitmap identified with a specific address, then it's just an efficiency. Should I say just an efficiency? It is an efficiency, right? So that's how we can improve upon the linked list. Okay? So then we start thinking about, okay, that's an efficiency, I got it, so I know how to manage the block number for getting a block number on the free list and stuff like that. But I'm still concerned with the fact that each of these methods is still pointing to a disk block, which is containing the free list. And the free list itself grows and shrinks over time, right? Because as I'm giving out data blocks, I'm reducing probably the number of data blocks holding my free list, right? Because as my free list gets shorter, I free up that node. That block can then be used as another data block. So I only want to use the numbers of data blocks needed to point to all of my free list. Does that make sense? Okay, so my free list itself is shrinking and growing. Which initially on the surface sounds okay. I erased it. Initially it sounds okay, but the problem we can get into, we said 256, right? So I have 256 data blocks here, 256 data blocks here. So I have 512. So I have 512 data blocks holding my free list, right? And that's full. So as soon as I get another data block to manage on a free list, I have to go get a new data block so I can then insert this new node on the free list. Well, if the next thing that happens is somebody's requesting a data node, then I delete it out of here and I delete this node. The next operation is somebody's giving me a free node or two, then I've got to go create another node. So instead of thrashing like this, shrinking and growing my free list, instead of doing that, when I go to create a new data node, why don't I just take some out of here and put them in here? Okay, so instead of just inserting one here, how about if I copy half of these? That solves the problem of deleting, inserting, and just flopping around on this data node here when I'm in that boundary condition. Because that's a lot of extra work, right? Getting a node, turning in a node, getting a node, freeing a node, getting a node, freeing a node, that's a lot of work. So to avoid that, because it does happen quite a bit, you do get to these edge conditions and that happens, what we found more efficient was, again, you just create the new one, but just go ahead and do the copy. It's okay. It's going to save us time doing these inserts and deletes. So you copy half of them over here, add that one additional one, off you go.
Wait, do you mean actually like physically copy or like move? Because you have 128, 128, so what would it be?
It was 256.
So, but you're moving half the nodes
Yeah.
into the other one.
So I just moved half of them over here.
Well, I'm saying it's not a copy. I'm splitting hairs because I want to be sure.
Yes. Yeah, it's not a copy, it's a move. Yes. And so I'm deleting, you just, then I worry about, okay, if this comes empty, so what? I've now got a half empty or half full, depending upon which camp you work with. Half empty or half full over here, no problem. Okay? So that gets there, so this is the condition that you can get into, and we do see it frequently, but the solution to that is doing exactly what we just talked about here. Great one. Move half of them over, off you go. Questions? The energetic ones amongst you are sagging. I think we're pretty close to saturation, and I really don't have that many more slides, so I think this is a good place to go ahead and break. And then what we will do on, yeah, is the question.